Hi, out of requests from people trying to work on the cross-course assignment, I thought I would make a quick video recording going over the example of how to calculate doubling time that we did in class on Wednesday. So just to review, here's the question that we did. If the doubling time for a bacteria population goes from an initial value of 10,000 to 10 million cells in 4 hours, what's the doubling time? So the first thing that we did was talk about how the data points that were given could be thought of as values in a table of values. So we have an initial population of 10,000, and then that grows to 10 million after 4 hours. The first thing that we wanted to do was use this information to fit to a curve y equals a to the bx. We know that coefficient a is the initial value. And so for our scenario here, a has to be equal to 10,000. So that means that our equation that we're building is of the form y is equal to 10,000 to the bx. The next thing we need to do is figure out our base value b. How we do that is we sub in our other point. We know we have an output value of a population size of 10 million when we have an input value or x value of 4. Subbing into our equation, that leaves us with just one unknown, that b value that we can solve for. The first step in solving an equation like this is to divide both sides by the coefficient. We would divide both sides by 10,000. 10 million divided by 10,000 comes up to 1,000. So we end up with a simplified expression or equation 1,000 is equal to b to the power 4. To solve for b, we have to ask ourselves, what's the opposite operation of raising b to the power of 4? And the opposite operation that would isolate for b is to take the fourth root. So if I take the fourth root of both sides, the fourth root of b to the power 4 is just b, and the fourth root of 1,000 well, that comes out to 5.623 and change. We'll keep it to 5 sig figs should be suitable. So that tells us that our equation that fits the data points is y is equal to 10,000 times 5.6234 to the power of x. Okay. I'm going to show you something here that we didn't go over in class, but how could we know that this is reasonable? If I was to try and visualize information that I was given in the question using a graphing software like Desmos, let's say, I could graph the point 0, 10,000 and the point 4, 10 million. And then I could draw the curve y is equal to 10,000 times 5.6234 to the power of x. And notice that my curve goes through both of my points. Excellent. So we know that that works and it fits the curve at those 2 points that we were given. The next step in calculating doubling time is to rewrite the curve or rewrite the equation in the form y is equal to a 2 to the rx. To do this change, we're substituting b equals to 2r. Okay, b we know is 5.6234, and what we're solving for is what that means r has to be equal to. Because we're solving for a value that's in the exponent, we can rewrite this in log form and then evaluate by calculating log of 5.6234 divided by log of 2. This tells me that r is equal to 2.4914 and change, and I could also fit a curve, an exponential curve that fits those two data points would be of the form y is equal to 10,000 times 2 to the 2.4914x. Again, how do I check that that's reasonable? I could go to a graphing software like Desmos and see that it fits my data at the 2 points. I could also compare it to my other curve that I just graphed and notice that my new curve, y is equal to 10,000 to the power 2.49144x, is exactly over top of our previous curve. It's just a different equation expressing the exact same thing. You can also see that if you evaluate 2 to the power 2.4914, it comes out to 5.6234. Okay. The last thing that we need to do to finish solving our problem is to actually calculate the doubling time. The equation to calculate doubling time is that doubling time is equal to 1 over r. So that means that the doubling time is 1 divided by 2.4914. Again, if I go to my calculator and actually evaluate 1 divided by 2.4914, I'll get an output of 0.401 and change. Sorry, I just cleared the display. And so that's telling me what my doubling time is in hours. Okay. If I wanted to check that again is reasonable, I could go to either of my previous equations and see what the population is at that point in time. If I sub in an x value of 0.40, it comes out to about 20,000. That's about how long it takes for the population to double. So we can check our work along the way and make sure it's reasonable. Okay. So again, to help us out, I'm going to do one more example where I'm just pulling some different values, a little bit smaller values, and then we can check and see how this works again. So I have population at 2 different times, and I know when t is equal to 0, my population is 5. When t is equal to 10, my population is 50, and I want to know how long it takes for my population to double. So the first thing I'm going to do is try and solve for my equation of the form y is equal to a to the bx. My initial value is 5, so I can figure out my a value right away. And then the next thing I want to do is substitute in the values associated with my second point. So when t is 50 or 10, or when x is 10, the output value, my y value, is 50. Okay. To start solving this equation, we divide both sides by the coefficient. 50 divided by 5 is 10. So I get 10 is equal to b to the power of 10. Okay. To figure that out, because my exponent is 10, I'm going to take the 10th root of both sides. The 10th root of b to the power of 10 is just b. The 10th root of 10 is 1.2589 and change. So I know that my equation is y is equal to 5 times 1.2589 to the power of x. It also tells me that my doubling time is more than whatever one time unit is that we're talking about here. Okay. The next step is I want to solve for the equation in the form y is equal to a to the 2rx. Okay, so I'm solving for when b is equal to 2r. My b value is 1.2589, and I want to figure out what that means r has to be equal to. Because I'm solving for an exponent, I calculate log of the number divided by log of the base. And when I go to my calculator tells me that r is equal to 0.33216. And so another way I could express the exponential equation that fits the data points that I was given is y is equal to 5 times 2 to the power 0.33216 x. To calculate my doubling time, I find the value of 1 over r. So it'd be 1 over 0.33216. So my doubling time in this case would be 3.0105 approximately, so about 3 time units. Okay. Again, so if we want to check that our answer is reasonable, we could try and visualize what the information that we were given. So we had an initial value of 0.5. We had a second value at 1050. We found after our first equation that we say the curve y equals 5 to the power 1.2589 x should fit at the 2 points, and we see that it does. And we say that the curve y is equal to 5 times 2 to the power 0.33216 x is equivalent. And I can see that those curves do indeed look the same. Moreover, we also say that the doubling time is about 3. And if I look at what the population is when x is equal to 3, it is about 10, which is double our initial value. So all of our information and analysis really does fit together, and you can check it. Hopefully going over that example that we did in class again is useful. And again, seeing a different example where the numbers turn out a little bit differently will also help you on the math assignment component of your cross-course assignment. If you have any questions, don't hesitate to ask. Good luck and have a great weekend.